Now today we are going to discuss about direction coefficient on a surface. In the case of curves in space, we are able to obtain a moving triad of mutually perpendicular unit vectors t, n and p, with the help of which we are able to express any vector at a point on the curve linearly in terms of t, n and b. Though we cannot have an exact analog of T and B at a point on the surface, but we are trying to have something similar to this triad at any point on the surface. So this is the preamble of this discussion. This led to the notion of tangential and normal component of a vector at a point P on the surface. For this purpose, let us consider R is equal to R uv be the equation of the surface and let P be any point on the surface. Then we know that the vector r1 and r2 are tangents to the parametric curves, and we have already established this result in the previous lecture, that v is equal to constant and u is equal to constant passing through P. Let capital N be the surface normal at P. Since R1 cross R2 is non-zero, neither R1 nor R2 can be a scalar multiple of the other, so that R1 and R2 are linearly independent. Further, capital N cannot be a scalar multiple of either R1 or R2. It means if n is equal to AR1, then n dot n is equal to AR1, and n is 0, which is absurd result since it gives 1 is 0. Thus, at any point P on the surface, there are three linearly independent vectors n, R1 and R2. Okay, we have to remember this sentence. Now, hence every vector A through P can be expressed uniquely as a linear combination of three vectors n, R1 and R2. Thus, there exist unique scalar an, lambda and mu such that A is equal to an n plus lambda R1 plus mu R2, that is equation number 1. Therefore, one expresses any vector through P as the sum of two vectors an, n normal to the surface and lambda r1 plus mu r2 laying in the tangent plane to the surface at P. On taking dot product with n on both sides of 1, we obtain a dot n is equal to an dot n is equal to an, as n r1 is equal to n r2 is 0. The scalar an is called the normal component of A. From this, it is easily seen that the vector lies in the tangent plane of A if and only if the normal component an is 0. The vector lambda r1 plus mu r2 laying in the tangent plane at P of the surface is called the tangential part of A, and lambda mu are called the tangential component of A. These components lambda mu depend only on the tangential part of A, and lambda mu are 0 if and only if the vector A is normal to the surface. Now, following definition emerges. First is the direction of any tangent line to the surface at the point P is called the direction on the surface at the point P. From the very definition of a direction on a surface, we see that there are infinitely many directions at each point of the surface. A vector A is of the form A is equal to lambda r1 plus mu r2. The components of the tangential vector A at P are lambda mu, so that we write A as A is equal to lambda mu. Lambda mu is a direction on the surface at P, means that lambda r1 plus mu r2 will represent a vector at P along a tangent to the surface at P. In all our discussion, components will mean tangential components, and the vector lambda mu stands for the tangential vector with component lambda mu. From the definition, we note that the following property: if A is lambda mu is tangential vector at P on a surface, then its magnitude may be re-expressed as under root E lambda square plus 2i f lambda mu plus g mu square. Further, from the definition, we have A is equal to lambda r1 plus mu r2. It means mod of A square, we can write lambda square r1 square plus twice r1 r2 lambda mu plus r2 square mu square. E we know ki r1 square, f r1 r2 and g r2 square. It means we may rewrite modulus of A is equal to under root E lambda square plus twice f lambda mu plus g mu square. Okay, thank you very much. Thank you. Stay safe.